this.
Does he talk like George does?
No, it's
isn't that George?
that mentality.
That challenge.
Do you want a bonus?
Do you have it? Anybody else have this bonus? Thank you. Last call for bonus.
Oh, yeah. Really? 2 whole people? Huh? Oh, you've only seen for a while for now.
All right, let's get down to business here today. I handed out 2 things to you. The first was a copy of problem number 10 from 2.6 that you did on WebAssign that caused lots of issues. I understand why it did. So I worked through it here. I'd like for you to just take time on your own time to take a look at that and see how it was to be done. I'm going to throw that problem out unless you got it right. If you got it right, I'll count it extra, all right? So I don't want to invest too much time on that because I won't give you anything like that on the test, on any test. I'll give you a problem like that perhaps to find the derivative of, but I won't ask you to find the equation of the tangent line at some weird crazy point like that one was. So that's the first thing. The second thing I handed you is a copy of the notes for 2.7. Specifically, there are problems in here that I don't feel like writing up on the board today. And so I plan on working through all these word problems today, but I'm just going to refer to them instead of writing them up on the board, okay? So everyone has a copy. And then I want to talk about our next exam. We are going to have an exam on Monday, next Monday. So, whoa. What's wrong?
We just started. Have you ever had that feeling of impending doom?
Every day, every day. Okay, so today is going to be 2.7. Wednesday will be more 2.7 and talk about the test. And then next Monday we'll have the test. And that test will cover, well, everything since the last test. So that's going to be pretty much all of Chapter 2. All of Chapter 2. All right, well, it has to happen eventually, so.
Then it can happen later, right?
I don't want to drag it on later because then it'll just be more on that test than perhaps you want. Okay. All right, so you ready to get down to business here? All right, let me just make sure my camera is going to get this. I hope you watched the videos for 2.7 because I'm assuming you did. We did problem, the problem that's cut off on the top of this page, we did that one in class. And I believe 2.77 we did not do. All right, so I'm going to start with 2.77 here. If the area of a circle is increasing at a constant rate of 1/5 a foot, square foot per second, how fast is its radius increasing when the area is 5 feet per second? So the picture that we have going with this is this one right here. And if you watch the video, right, then what I was trying to explain here is that our area is the thing that's changing at a constant rate instead of the radius. So can someone explain to me what's happening in the picture? Anyone?
It's getting slower.
What's getting slower?
The rate of change.
Of?
Area or radius.
Which one is it? The rate at which the radius is changing is actually slowing down. The rate at which the area is changing is constant. So in order to kind of maintain the proportion, we're adding the same amount of area per unit time. But that forces us to grow slower as time goes on. So we want to know at a specific time, 2.77, if the area of a circle is increasing at a constant rate. So here I have a constant increase of area of 1/5 square feet per second. Then how fast is the radius increasing at exactly the moment the area is 5 square feet? So at exactly the moment that the area is 5 square feet, which is way in the beginning. I don't know if I can actually get to it. Let's see. Let me try and get to when the, well, right about somewhere in there. See, the area is about 5 feet, 5 square feet. So right about at that point in time, somewhere around there, at that instant, how fast is the what? Radius increasing at that instant. Okay, so the set of steps that are given to us in this section are to, first of all, do what? Draw a picture. So the first step is to draw a picture of the exact moment in time. So the exact moment in time is going to be when my circle has a what? A fixed radius, doesn't it? But I don't know the radius, do I? All I know is that at that specific moment in time, my area is 5 square feet, right? The area? So I'm going to put here below this picture that the area at this moment in time is 5 square feet. If you know the area, can you determine the radius? If you know the area of a circle, can you tell me what the radius is? Yes. Okay, so I'm going to keep that in mind. All right, I'm going to keep that in mind. I'm just going to write down my picture right now. But that's my circle fixed in time with an area of 5. My second picture should be a picture of the circle at any given point in time. So there my radius is allowed to change, right? So I'm going to label it R. That may not make a big difference in this problem, but as we move on to do more of these, you'll see how these two pictures are important to draw them separately. Just remember, this one's stuck, it's not moving, this one is allowed to change, right? So what's the third step? Write down what you're given, write down what you want, and start to assign some variables to things. So what are we given in this problem? Constant rate of change of what? The area, right? So I'm given the rate of change of area, which we said is like the speed of the area. The speed is a derivative. So I'm given the derivative of the area. So how do I write that? dA dt. And it's given to me to be what? 1/5. And then you can put the units here, square feet per second. But that's my change in area with respect to time. That's given to us. What else is given to us? A specific point in time, right? The area is 5. Let me get to the area being 5 in a second. Even though that's given to me, what is it that I want? What is it that I want? The rate at which the radius is changing, right? So I want the rate, not just the radius, the rate. So dr dt, right, is what I want. And watch this. When do I want that? At exactly the moment what? The radius is, or not the radius, sorry. The area is 5. Does that make sense? We are told that the area is changing at a rate of 1/5 square feet per second. I want to know how fast the radius is changing at exactly the moment that the area is 5 square feet, if you want. That's what I want, right? Anything else I'm missing there? I think I've got it all pretty much. So what is the fourth step then? Find an equation. And this equation is supposed to do what? Relate what we want to what we're given. And what we want here is dr dt. What we're given is dA dt. So we want an equation that relates area to radius, which we know, right? So our fourth step, what equation relates the area of a circle to the radius of a circle? Area is pi r squared. That's the connection we need to make. So once I know what the area is, or the equation is, what do I do?
Get r minus 1.
You don't have to do that though.
Get the derivative.
Just take the derivative, implicit differentiation. Is this step 5? I have the steps written down. Is this step 4 is get the equation. 5 is implicit? Okay. So step 5 would be implicit differentiation. So take the derivative of this. What's the derivative of area with respect to time? dA dt, which we're happy about, right? Because that's part of what we're given. And then on the right side equals, pi is a constant, so here's my pi. Just bring it down. And then what's the derivative of r squared with respect to t? So power rule first, right? 2r times the derivative of r, dr dt. So there we had to use power rule with chain rule, right? Power came down, but then derivative of what's inside is dr dt. So now let's actually figure out what dr dt is, right? Here it is. I know dA dt, right? And this is step 6. It says like plug everything in now for the instant in time. So I know what dA dt is. I like to go through this and kind of like circle the things that I have. I know what dA dt is, so I'm happy about that. I actually want to know what dr dt is, so I'm happy about that. But r, I don't have the radius, right? What I have at the instant in time is the area. So what I'm going to need to do is use this area to create the radius, now that I can fix everything in time. Do y'all understand that? I need r. So now that everything is fixed, if you have an area, if I have a circle that has an area of 5, then, and I know that the area is pi r squared, then if I replace area with 5, I get that 5 equals pi r squared. Dividing through by pi, I get 5 over pi is r squared, which means that r is the square root of this, isn't it? So I can now come in here and I can rewrite dA dt is what? 1/5 must equal pi times 2 times square root of 5 over pi times dr dt. So all I've done is I replaced dA dt with what I had earlier, replace r with this, solve that for r, got that. Any questions on what I did there? And now all I have to do is isolate dr dt, get it by itself on one side of this equation. And these are all numbers, aren't they? These are all just numbers. Let's see if you can follow what I do on the next step. Let's see if you can follow this. You tell me what I did. 1/5 equals square root, let's see. What happened? So I forced the 2 pi into the root. When you put things into a root, what happens to them? They get squared on their way in, right? So when you square the 2 on its way in, it becomes a 4. 4 times 5 is 20. When I take the pi and I send it through, it becomes pi squared. But pi squared over pi is just pi. So I have a 20 pi, root 20 pi. Now I'm going to divide both sides by that square root. So I'll have 1 over 5 root 20 pi equals dr dt. And that's an exact answer right there. I'd be happy with that. You can mess with that a little more. Like you could take that 2 back out and make it a 10. But That's the exact answer. To find out what that number is numerically, we would probably want to use a calculator now and get a decimal, which I'm going to do because I think it's important for us to actually have an idea of what that rate is as a numerical value. So I'm going to take 1 divided by 5 times the square root of 20 pi. On my calculator, I get approximately that this is 0.0252 approximately dr dt. Now, what about units? That's a rate of change, isn't it? So what are my units for that rate of change? How did I say last class to figure out your units? Take a look at the 2 letters here. R is a what? Radius? What's the radius measured in? Feet, right? What's your unit of time? Seconds. So this should be in feet per second, just feet per second. So your final answer is 0.0252 feet per second. That is the approximate rate of change of radius with respect to time at that exact moment in time. Is that okay? I want to show you something slightly different than this. Let me just make sure that came out okay. I like that, yes. Let me show you something. We had, what was the derivative that we had? At the very beginning it was dA dt equals 2r times dr dt, right? That was our derivative? No, I'm missing a pi. 2 pi r dr dt. Yes? That's what we had, and then we plug things in? Just follow me here. I'm going to solve for dr dt by just dividing both sides by 2 pi r. So here's what I'm saying. The change in radius with respect to time is this. Do you all agree with that? What did we say should happen as this gets bigger? As the radius gets bigger, what should be happening with how fast the radius is changing? It should be slowing down, shouldn't it? Right? If the area is changing at a constant rate, then the bigger the radius is, the slower it should grow. Look at this ratio right here. This is the rate at which the radius is changing. What happens if I let the r here get big? What happens to this fraction? It gets small, doesn't it? As r gets big, if that's constant, right? Then if that gets big, this gets small. So the bigger radius gets, smaller this gets. I just want you to see that relationship. We can see the relationship in the equation before we even plug things in. So it matches what we kind of see geometrically happening.
So the rate of change is approaching 0.
Exactly, right? If you let the radius go to infinity, then the change in your radius approaches 0. Of course, it would never be 0, but it would become infinitely small change in radius. So you almost have a connection there with limits if you want. Okay, let's look at the next example. Does everyone have a copy of the questions? Okay, so the next example that we have is 2.79. So what we do in this problem is we change from a circle to a sphere. And it says that if the radius of a sphere is increasing at a constant rate of 2 feet per second. Here, you change that. Oh, there we go. Okay, so that's 3-dimensional. It's kind of hard to see it, but that's 3-dimensional. It's a sphere. And it's growing where the radius is growing at a constant rate. And so the volume is changing over time, isn't it? As time goes on, the volume changes. But if you watch the video, we talked about or I talked about the fact that for every step in the radius, the volume gets bigger by more and more each step. So we want to know at a certain instant, how fast is the volume increasing? So it's the same sort of idea, except we're looking at a sphere instead of a circle. Okay, so let's set this problem up. 2.79. I'm going to draw two pictures. The picture at the moment in time is a sphere. Here's one way to draw a sphere like this. And I, of course, have some radius to that sphere, right? But at the specific instant in time, what can you tell me is fixed? The radius, but the numerical value I'm given is what? It has a fixed volume, right? The volume in this picture is what? 36 pi, right? That is, and that's cubic feet. That is the picture of my sphere at the moment in question. Now let's talk about the general picture. The general picture is this, with some radius and some volume, and they're changing together, right? Radius changes, volume changes. That's a little r right there. By the way, if I know the volume is fixed in this first picture, then the radius is fixed also, right? There is a specific radius that corresponds to this volume. I could solve for radius if I wanted, right? If I wanted to. Okay, I'm not going to, but just keep that in mind. All right, what's the third thing? What are we given? What do we want, right? What are we given?
Constant rate.
Constant rate of what? The radius, right? The radius of the sphere is increasing at a constant rate. So that should be dr dt, right? And it's given to us to be 2 feet per second. Now go to what you want. What do you want? How fast is the volume increasing? So you want dv dt, right? dv dt. Anyone have a question on this? Right? Anyone have a question on this? Yes? That's the derivative, because they say, how fast is the volume increasing? See, this would be what makes this a calculus problem is the fact that they want to know how fast something is changing. Whereas in a college algebra problem or something, they would be like, what's the volume if the radius is this? But there's nothing is actually changing. It's not growing or shrinking, it just is. So it's a rate, dv dt. When do we want this? At exactly the moment what? At the moment that the volume is 36, right? Pi? That's when we want. Okay. Any questions? Step 4. Equation. Give me an equation. Someone tell me what equation I'm going to need. Volume of a sphere, right? And I need to hope that that volume of a sphere formula has what two variables in it? Radius and v, right? Volume and radius, because I'm trying to connect the radius and volume together. In every problem we've done up to this point, I've always been able to find an equation pretty easily, right? It's not going to be like that all day, all right? As class goes on, these equations are not just going to be sitting there for you in a book somewhere. We're going to have to create the equations ourselves, all right? So, what is the volume of this sphere? Volume of a sphere is 4/3 pi r cubed. In calculus 2, you will prove that formula. You will actually show where it comes from. Okay, so there's our formula. Now we check it. It has v and it has r in it. If the only two variables are v and r, then I guarantee it, if I do my derivative correctly, I should get a dv dt and I should get a dr dt. Now I just need to differentiate. So I'm on step 5. So on step 5, differentiate this. It's what? Why don't you get the derivative real quick? I'll give you just a minute to try and write it down. And I'll put the answer on the board, and then you can see if it matches. How many of you got this without looking up at the board? Were able to get that? Yeah? Okay.
How come the 4/3 pi doesn't just go to 0? I know we write it like that, but I just don't know why it doesn't turn into 0 like other constants.
Okay. Good question. Why not? It's in front of a function. The whole idea with derivatives and constants was that if the derivative of a constant by itself is 0, but the derivative of a constant which is attached to something else, a function, through multiplication, then that will follow through.
It's like the rest of it just turns to x and it's like that.
The derivative of a constant times a function is the constant times the derivative of the function. That was one of our rules of differentiation. The derivative of a constant by itself is 0. That's what it is. So you look at the 4/3 pi as a constant in front of a function. That is a function because it involves a variable that we don't have control over. It's changing, right? So I treat the r cubed as a function. There's my constant comes down in front of it. Is that okay? Okay. Now I can clean that up a little bit, right? Do y'all see the 3's cancel? That I can do. So I can have something like dv dt equals, let's see, just 4 pi r squared dr dt. So let's go through a little checklist of the things that we have here. How about dv dt? Are we given that in the problem? No, but that's what I'm actually trying to find, isn't it? So I'm okay with this. I have that, I'm happy. How about r? I don't know the radius, but I can find it because now I can fix the sphere in time. How about dr dt? I have that. So the only thing I need to figure out right now is what r is. So here's how I'm gonna get r. I'm gonna go back to my volume formula, but now I'm going to actually let my volume be what it is at the instant in time, which is what? 36 pi, right? That's my volume at the instant in time. That must equal 4/3 pi r cubed. I need to solve that for r. So how about dividing both sides by pi, just to get the pi's out of there? How about multiplying both sides by the reciprocal of 4/3? Because if I multiply this side by 3/4, it's gone. If I multiply the left side by 3/4, I get a new number, right? So I'm multiplying both sides by 3/4 there. What's the left side become? 27? You could go this times this divided by 4, or you could go 36 divided by 4, which is 9, then times 3, which is, I think, a little cleaner. 27 is r cubed. Y'all see that? Question? No? You okay? You sure? It's kind of that glare of, if there's like one little thing that's missing, it can be really hard, right? Just, you got to let me know if there's some little thing that's missing. So what's r? 3, right? It's the cube root. You take the cube root on both sides. And so the cube root of 27 is 3. So your r is 3 at this particular moment in time. Now I can come back over here and I can replace that r with 3. And I should be able to solve and get dv dt. So dv dt is 4 pi times r, which we just said is 3. So 3 squared is 9 times, what's dr dt? in this problem. It was given to us to be 2, right? So times 2. So what is that? 3672 pi? dV dt is 72 pi. That's the exact answer. Give me the units. Volume is cubic units, right? Feet cubed per time second. That's the exact answer. If you wanted to, you could get a decimal approximation by multiplying 72 times pi, and you get some answer.
For the test, do you want it like that?
I'll take either way. But you should always have the exact answer. The exact answer is where you don't round. As soon as you type that in the calculator is going to round it. Approximate it somewhere. All right, what do you think? This okay so far? Why is it that when I started the problem and I wrote down the formula for volume, why did I not replace the R with 3 here before I differentiated? It has to be changing, right? If you fix the radius to be 3 before you differentiate, then the derivative is going to be 0. Because once you fix the sphere with the fixed radius, it's not changing. Remember I was saying, like, when I'm running across the room, you can talk about my speed, but if I just stopped, right, already, I don't have a speed. So that's why you cannot replace that with your given information for the instant in time until after the differentiation has occurred. That's the power of all this, all right? That's what makes this thing so great. Okay, next problem. Expanding sphere. We just did, how about the next one? 2.711. This time you have a sphere whose surface area is increasing at a constant rate. So what happens here is just like the circle. To maintain a constant change in surface area, it has to slow down as it grows. The radius has to slow down. So in the beginning it grows fast, and then as you go out it gets slower and slower and slower. How many of you, by show of hands, think that you could set this one up and get this going? Just, I want to see how many people feel comfortable with this yet. A couple? All right, let's walk through this. Step 1. I'm doing 2.711. If the surface area of a sphere is increasing at a constant rate of 20 square feet per second, how fast is the volume increasing when the volume is 36 pi cubic feet? So my instant in time is pretty much the same as it was before, right? 36 pi? Oh, wow. That's my instant in time. My general picture is a sphere that's growing, so it has some radius that's changing. What I'm given in the problem is, and what I want is what? So what am I given? Let's do this. I'm given the rate at which the surface area is changing, right? It is d, then I call it d what? Yeah, dSA. You can call it whatever you want. I'm going to call it dA. And we'll just understand that the A I mean is the surface area. Okay? I'm talking about the surface area of a sphere. Not the area of a circle, surface area of a sphere. That is going to be what in this problem? 20 square feet per second. What is it that I want? How fast its volume is increasing, right? So d v dt, right? I want to know what that is when? At exactly the moment that the volume is 36 pi. So that's almost the same setup as last time, isn't it? Just about. Except, what are the two things that we're trying to connect together? Surface area and volume, not volume and radius. So is there an equation sitting in your book or something like that that connects volume and area together? There's not. See, this is the first problem that we've run into where it's not just, oh yeah, volume is 4/3 pi r cubed, or oh, you know, surface area is this. So now we're going to have to do a little work to make the connection between these two variables. So let's see what work we're going to have to do. What equations do you have for surface area and volume? So for a sphere, all right, for a sphere, we already know the volume of a sphere is 4/3 pi r cubed, right? And what is the surface area of a sphere? Not area of a circle. I'm just going to use A for surface area of a sphere. 4 pi r squared. You should have formulas. This is a new book, right? The book you have is new? You had to buy a new one? It should have that little tear out sheet somewhere. Yeah, it should have here the little pictures of some of the common geometric shapes there. In the very back. It's the first little tear out page. 4/3 pi r squared. Now, we have a couple of options here, all right? This is going to be extremely interesting, I think, to show you this for the first time. In last class, I think it was last class, what we did is we created a new equation. Do you remember that? And what I did is I solved this one for r, and then I replaced that one into here. Remember that? I'm going to do something completely different now to show you just how amazingly powerful this can be. All right? Just watch me. Do you agree both of these equations have the letters we want, area and volume, right? But they both include radius, which we don't have any information about the radius here, right? And if I differentiate this, right, if I do, I'm going to get a dv dt, which I'm good, right? But I'm also going to get a what? A dr dt, which I don't like. Because I don't know anything about dr dt, do I? And in this one, if I differentiate, I'm going to get a dA dt, but I'm also going to get a dr dt, right? So just check this out. This is going to, I think for some of you, you're going to, maybe you'll get little goosebumps from this, maybe not. Okay, dv dt, I'm differentiating both right now, watch. We already know the derivative of that would be 4 pi r squared dr dt. So I already did the 3 came out and canceled and cleaned it up, right? That's what we had earlier. So I'm going to put my little squiggly under this. I differentiated that. Now watch, what would happen if I differentiate this one with respect to time? dA dt, right, equals what? 8 pi r dr dt. Do you agree with that? Now these are two separate equations, aren't they? Yes? What is it that we're trying to solve for? We wanted what? dv dt, right? So this one already has dv dt sitting right here, doesn't it? All I need to know in order to answer the question is the radius. Do I know the radius at the point in time? Can I find it? Yes, right? I can fix it and I can figure out radius. Do I know dr dt? No, right? But look at this one. Do I know dA dt? Yes. Do I know r? Can I figure out r? Yes. So that means I can figure out what dr dt is. Can't I? I can use dA dt and I can use the r to find dr dt and then use that dr dt right there. So I've connected the two together. So you kind of have some options here. I'm going to do it this way. I'm going to just replace this one. What's dA dt at the specific moment in time? It was 20, right? That was the change in area over time. Equals 8 pi. Now radius. I need the radius. I'm going to have to do some scratch work here. Let me do it right underneath this one, okay? Remember that at the moment in time, what was my volume? 36 pi. And volume is 4/3 pi r cubed. Didn't we already do this in the previous problem? What did we get when we solved for r? We got r was 3, right? That's what we did in the previous problem?
Yes.
So I'm not going to do that again. So that means I can replace this r right here with what? 3. And then that's dr dt right here. So now dividing through, let's see, 8 times 3 is 24, right? So I get 20 over 24 pi is dr dt. I can reduce that fraction. What goes into both of those? 4? 5 over 6. So 5 over 6 pi equals dr dt. How are y'all doing? Are y'all with me on this? So now what I do is I take this, which to me now is just a number, dr dt, and I'm going to bring it back over here now. And I'm going to figure out what dv dt is. So going to this, I get that dv dt, change in volume with respect to time, is equal to 4 pi. Radius we already know is 3, right? Radius is 3, so 3 squared is 9, times the dr dt, which I know is 5 over 6 pi. And I get pi's to cancel there, right? I have a pi here and a pi here. 20 times 9, right? 180 divided by 6, 30. dv dt is 30. 30 what? Cubic feet per second. So I think that was a great problem. I liked it, but I'm going to show you how to do that problem a different way. Because I think you should feel comfortable. Not that you have to feel comfortable anyway, but I know when I was a student, I was shown a certain way, but then as I developed my skills more as a tutor, I realized there are more than one way to do these things. So it's always nice to see different ways, I think, because you kind of find the way that you like that makes most sense to you. So let me go back to the problem where we were like right at this point instead. And let me just take the first two equations and no differentiation here. I'm going to solve this one for radius. So there's just dividing both sides by 4 pi. And then I take the square root, so I get square root a over 4 pi is the radius. Right? Now I come back over to this formula here. My volume is 4/3 pi times my radius, which is the square root of a over 4 pi, but then all of that what? Cubed. Do you agree with that? That's just the radius, which is this, cubed. Now if I just play with this a little bit, this is volume equals 4/3 pi of, to take the square root of something and cube it is the same as taking it and raising it to what power? The 1/3 would be cube root, but this is square root then cubed. So it would be to the 3 halves. To the 3 halves. The 2 is the square root, the 3 is the cubed. Y'all follow me? Now, watch this. Volume is equal to 4/3 pi times 1 over 4 pi to the 3/2 times a to the 3/2. All I've done here is I've realized that I have a fraction to a power. So I split it where I take the power on the top and the bottom and then peel the denominator off. Why? Because what is 4 pi to the 3/2? Isn't it just a constant? Isn't that just a number? I'm trying to pull everything away so that I have my a by itself. Now I'm going to differentiate. So what's the derivative of this? dv dt equals, this is all a constant, right? This is all just some constant? 4/3 pi times 1 over 4 pi to the 3/2 times, what's the derivative of a to the 3/2? 3/2 a to the 1/2, drum roll, dA dt. And now you have dA dt, which is what you were trying to figure out, isn't it? And you've got dV dt, or no, it was dV dt is what we were trying to figure out. dA dt we're actually given in the problem, weren't we? But what would we not have? A. So how would you get A? You know what the volume is, right? So you'd have to go solve for A. This way looks a lot harder, doesn't it?
Yeah.
So I'm not going to continue. I'm just going to say dot, dot, dot. We would get the same answer. But you see how that setup's completely different? I think that's a little harder to do, though. Okay, let's move on to the next example. 2,713. I like this problem. A plane is flying overhead. Is that where we are? Yeah. A plane is flying horizontally at an altitude of 2 miles and a speed of 600 miles per hour. The plane is headed directly over a ground-based radar station. At the moment the plane is 6 miles from the radar station, how fast is the distance between them changing? So this is the picture I had done for you. So that's my plane, right? The red dot is flying over the radar station. Here's my radar station. The red line, can y'all tell that's red? Yeah. The red line connecting the two dots is changing, right? As time goes on. And that red line is the distance between the plane and the ground. So what we want to know is at exactly the moment that the plane is 6 miles from the radar, how fast is the distance between them changing? So there's some point in time where the distance right here is 6. And at that instant, right then, how fast was it either shrinking, right? Because over here, isn't the distance getting smaller? Smaller, smaller, smaller. And then once it goes past the radar station, it's getting larger and larger and larger. So at exactly the moment that the plane is 6 miles from the radar station, which is right then, that's when it's 6 miles, exactly then, how fast was that red line shrinking? Okay? Everyone understand the picture? Yes?
Couldn't you get two answers? Positive and negative?
Yes, you could. It's all going to depend on how we draw our picture. Okay? So how do you want to draw? You want to draw this situation, or do you want it on the other side of the... Right here? Let's do it this way. And then maybe after this, we'll look at it the other way. Okay? Just to at least set it up. It will matter. We'll change the sign of our answer.
That's it?
That's it.
Okay.
Yep. But there's some other subtleties that we would have to pay attention for. Okay, you know what? At this point right now, I need to stop my video real quick and restart it.